Hello everyone, I am Dr. Fawzul Atik. We are in the series of the lecture Discrete Mathematics course, and we are in the last unit. In the first lecture, we discuss about the graphs, then vertices, edges, degrees, and then finally we have discussed the handshaking theorem. What was that? Sum of the degrees of the vertices is equal to 2 into number of edges. Therefore, from the previous lecture, we understood that sum of the degrees must be an even number. Right. Now, following that, I have a result, and look at that. An undirected graph has an even number of vertices of odd degree. Now, this is always true. Why? An undirected graph has an even number of vertices of odd degree. That means number of odd degree vertices is even in case of a undirected graph. Why? Because this will follow from the handshaking theorem. Why? Because suppose you divide the vertices. This is the even degree vertices, set of all even degree vertices, and V2 is the set of all odd degree vertices, right? And then if you do the degree sum V belong to V, which is by handshaking theorem it is 2m, that means it is an even number. Now if I divide the two sets, so first you take the even degree vertices, degree of V, where V belongs to V1, all the even degree vertices are there, plus sum of all the odd degree vertices, where V belong to V2. Right? Here each quantities are even number. Here each quantities are odd number, and I am taking the sum of it. Now if I have, or if I add all the even degrees, if I sum it, what will get? I'll get an even number. Correct? If I add, and I know that this sum is also an even number. And here all of them are odd numbers, but the whole sum is what? Because this is even number, this is even number, so this sum is actually even number minus even number, which is an even number. Right? That means this one is also an even number. But when it is possible, these are all of them are odd degree case. Nah? That means they are like 3, 3, 1, 1, 5, like this. But like, will it make it even? When it can make it even? If you have, because all the single entries are odd number, but their sum is even. When it is possible? Whenever you will have even number of odd numbers. Now it is possible. 1, 2, 3, 4, 5, 6. Not possible. But if I make it this 7, no, it is not an odd number. So definitely it should be an even number of odd numbers you have. What are they? That means in a graph you have even number of vertices of odd degree. Is it clear? In a graph, you have even number of vertices of odd degree. The whole proof is involved here. So suppose V1 and V2 be the set of vertices of even degree and set of vertices of odd degree. Then by handshaking, 2 into m is equal to 2 into number of edges is equal to sum of the degrees. But sum of the degrees, because vertex set even degree vertices and odd degree vertices. But this is even number, this is even number. So this one must be even number, the whole sum. But the whole sum, each content is odd number. So there should be even number of odd numbers. Therefore, the number of odd degree vertices is even number. The proof is here. The detailed proof is here. I hope you understand. Okay. The next one. Adjacency in directed graph. Now, if U and V are edges because till now we discussed the adjacency in the undirected graph. But if you have a directed graph, what will happen? So if U V n is an edge in a directed graph G, then U is said to be adjacent to V, right? So if U starts at U and like this, if you have U V, then U is said to be the adjacent to V, correct? And U is said to the initial vertex, V is the terminal vertex or end vertex, right? U is said to the initial vertex and V. So UV is like that. U starts from U, ends at V. Then U is said to be the initial vertex, V is the terminal vertex. The initial vertex and terminal vertex of a loop are the same. Yes, it is the same if I have a directed case also. Now in this case, we will not have the degree, but we will call it as in degree and out degree. What do you mean by in degree? In degree in case of a directed graph. So in degree of a V is denoted by D minus V is the number of edges directed towards V, right? So that means number of edges directed towards V. Like this. How many edges are there? That is called the in degree. Number of edges directed towards V. Out degree is what? Number of edges directed opposite to V. It is denoted by D plus of V. directed number of edges directed opposite to V. So like this, like this, like this, how many edges you have? So in this case, it is 3. And note that a loop at a vertex contribute 1 to its both its in degree and 1 its out degree of the vertices, right? Now I'll give you an example of a graph, maybe a small graph I'll do, and which is a directed graph, which will be of directed graph, and it can have this kind of loop also. It can have multiple edges possible. So I'm writing it as A, B, C, and D. There are 4 vertices are there. Now in degree, how do you define in degree? The degree minus of A and degree out degree of A. We define it, we'll denote it by this. So degree minus of B and degree plus of B. Degree minus of C, degree plus of C. Finally, degree minus of D and degree plus of D. So in degrees and out degrees of all vertices we'll calculate. Now see how to calculate the in degree. In degree is the number of edges directed towards B. So how many edges are there directed towards A? There is no edge. So in degree of A is 0. How many of edges are there directed opposite to V? That is called out degree. It is 2. So there are 2 in degree, out degree of A is 2. Similarly, you find the in degree of B is what? In degree of B is 2. Out degree of B is 0. In degree of C, how many edges are there directed towards C? There is 1. And directed opposite to C is 2. In degree of D, now see how many edges are there directed towards D. This is 1, 2, and because of the loop, 1 more. So there is 3. And directed opposite to D, it is 1, and because of the loop, 1 more. So 1 plus 1, it is 2. Right? So this is how your in degree and out degree will be defined. So if you have a loop, it will contribute degree 1 to its in degree and degree 1 to its out degree. I hope this is clear. Now we will try to find out that what will be the handshaking lemma in this case. Now you just add all the degrees, all the in degrees. What is the value? It is 6. Add all the out degrees. What is the value? It is 6. And check how many number of edges you have in the graph. 1, 2, 3, 4, 5, and 6. So number of edges is equal to sum of the in degrees. Number of edges equal to sum of the out degrees, which are equal. Right? So in case of a directed graph, that handshaking lemma, like the form is number of in sum of in degrees equal to sum of out degrees equal to number of edges in the graph. I hope this is clear. Okay. Next, we have some particular type of a graph. The first one is complete graph. A complete graph on n vertices is denoted by Kn, is a simple graph that contains exactly one edge between each pair of distinct vertices. So complete, from the word itself, you should understand that something is complete, right? So what I will do, I'll draw a complete graph K4. So I should have 4 vertices, and you have to keep on adding edges till now it is complete, right? So by keep it simple. First of all, it is a simple graph, no loop, no multiple edges. Then you keep on adding. So I'm adding some edges here. I added here. Still I can make some edges, right? So I added edges here. I add edges here. I add edge here. Still it is possible. I add one more edge here. Till now all the edges I have done, and it's a simple till now. But can you add one more edge? No more edges is possible, right? So this edge, adding edge is complete. So this graph is an example of a complete graph K4. So it contain exactly one edge between each pair of distinct vertices. See, each pair of distinct vertices, there is an edge. So this is a complete graph K4. Similarly, if you have understood, can you draw a K5 graph? So you will have 5 vertices, and you have to keep on add it until it is complete. So add each pair of edges in it. See, I'm done. You cannot add one more edge. So this is K5, example of K5. Clear? Now, similarly, you can able to draw K6, K7, K8, K10, anything. Clear? Now, if the V of K4, that means V of K4, what is the number of and the cardinality of it? How many number of vertices are there in K4? It is 4. Number of vertices in K4, it is 4. And how many number of edges are there in K4? E of K4. Now see, you are basically finding out that an n element set you have and you are adding each pair of vertices. So n element vertices you are adding each edge between each pair of vertices. So basically you have to find all the two combinations from a set of n elements. How many ways you can do? It is n choose 2 or nc2 way, right? So therefore, 4 vertices you have to find out all pair of vertices. 4c2, which is 6, and you see that there are 6 number of edges are there in K4. 1, 2, 3, 4, 5, and 6. So E of K4 is 6. Similarly, E V of K5, number of vertices in K5 is what? 5. Number of edges in K5, it is 5c2, which is 10. Right? You can check, there are 10 edges are there. 1, 2, 3, 4, 5, then 6, 7, 8, 9 and 10. There are 10 edges are there. So if you have understood that, then can you tell me how many number of vertices are there in Kn and how many number of edges are there in Kn? So number of vertices in Kn is definitely it is n. Number of vertices edges in Kn is what? Nc2. Nc2 means what? It is basically Nc2. The value of Nc2 is n into n minus 1 divided by 2. Now, if I ask how many number of edges are there in K100, you will say 100 into 99 divided by 2. Clear? How many number of vertices are there in K200? Number of vertices in K200 is 200. Clear? I hope you understand. You can able to draw K6, K7, K8, any graph, complete graph. Okay, the next one. Next one is a cycle. Now, cycle means what? Cycle, like from the word itself, it's a kind of circular type of a thing, right? Circular type. You start from one and end at the same thing. That is called a cycle. So I'm drawing some cycle graph and then we'll come to the definition. So first I'm drawing a cycle graph C4. So cycle graph C4 is actually like this. The cycle graph C4 is like this. 1, 2, 3, 4. I'm giving the name as 1, 2, 3, 4. This is the cycle graph C4. That means you start at 1, go, and come back to the 1 again. That is a cycle graph C4. Now, if you have understood, can you draw a C5 graph? C5 will have 5 number of vertices. So I'm drawing that. And then start from this, go, and come back to the same. This is cycle graph C5. Then cycle graph C6, I think you can easily draw that. There will be 6 number of vertices will be there. Start, go, and come back. This is an C6, example of C6. So this is how you can draw. Now, if you have like now, this is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5, and 6. See the vertices. What are the edges? 1, 2, 1, 2, 2, 3, 3, 4, and 4, 1. Similarly, 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1. Therefore, in Cn number, what are the edges? 1, 2, 2, 3, 3, 4, n minus 1, n, and n1. Right? So I hope this is clear. And if you have understood, you can easily say what is the number of vertices in Cn? Definitely it is n. And how many number of edges are there in En? It is also n, because you can easily verify that. I hope this is clear. The next one. Next one is a wheel graph. What do you mean by wheel graph? A wheel graph Wn is obtained by adding an additional vertex to a cycle Cn, and that connects. So from the word wheel itself, it's like a wheel, right? Where you will have a outer ring and there will be a center in it. So where all it is connected with everyone. So wheel graph, first you have to draw. I am drawing a wheel graph W4 first. So for that, I need to draw a C4 in the beginning and add one more center in it. And from the center, add all vertices. This is the wheel graph W4. Right? Similarly, how to draw a W5 graph? Draw a W5, draw a C5 first, draw a C5, then make a center of it. From the center, add all the edges. Done. This is a W5. If you have understood what is W6, you can able to draw, right? And you check how many number of vertices there in W4. Number of vertices in W4 is 5. Number of vertices in W5 it is 6. What is the number of edges are there in W4? 1, 2, 3, 4, 5, 6, 7, 8. So 8. 2 into 4. W5, like outer ring have n, and from the center to all vertices is again n plus n to n. So if you have understood, tell me V of Wn. How many number of vertices will be there in Wn? It is n in the cycle plus 1. So n plus 1. How many number of edges are there in Wn? So in edges is from the outer ring you have n, and from the center to n edges. So therefore it is 2n. I hope this is clear. Then we have the n-dimensional hypercube, or the hypercube graph Qn, right? And it has 2 to the power n number of vertices. So this one we can do it easily. So it's an n-dimensional, right? So one-dimensional things is what? So this is an one-dimensional hypercube Q1, because this is one dimensional. So it has 2 vertices. What is Q2? How to make Q2? Q2 is take 2 copies of Q1. Take 2 copies of Q1. This is one, and another Q1. So I have taken 2 copies, and then adjacent the corresponding vertices. This is Q2. What this is 2-dimensional. Now see, this is a 2-dimensional thing. No? It's in a plane. This one is 1-dimensional. This is 2-dimensional. Now how to make Q3? Q3 is it's 3-dimensional hypercube. So take 2 copies of Q2. So 1, and then another one is I have taken 2 copies of Q2, then add the corresponding edges, vertices. See, I got a 3-dimensional figure, right? This is a 3-dimensional hypercube or Q3. Similarly, I can draw Q4 also. I can draw Q4, but it will not look nice. What I have to do? I have to add this 2 Q3 here. This is Q3 and Q3, and then add the corresponding edges. So Q4 I'm not drawing, but I hope you understand. So number of vertices in Qn is 2 to the power n. Up to that, if you learn, that is enough for the time being. I hope it is clear. So some few special type of graph we have learned. Now we have one more special type of graph called a bipartite graph. Bipartite. Bi means what? We all know bi means 2, right? Partite. Partite means what? Some kind of partition I'm doing. So bipartite graph is, so if graph you will partition its vertex set by maintaining something. How do you do that? So if the vertex set you divide into 2 parts, one is V1 and another is V2. So you divide the vertex set, if it is possible that you divide the vertex set into such a way that you divide into 2 parts, such that some vertices will be here and some vertices will be here in the graph. And edges are from V1 to V2, right? Edges are only from V1 to V2. Only from V1 to V2. Edges are only from V1 to V2. No edges should be there within the set V1, right? No edges should be there within the set. So this edge is not possible. This is not allowed in case of a bipartite graph. So within the set, suppose this there is an edge. This is not allowed, right? Only all the edges should be from one set to the another set. All the edges should be from one set to the this set to the this set, but not within this set, not within this set. That kind of partition if you can make in the graph, you call the graph is a bipartite graph. And this partition set V1 V2, this partition set V1 V2, you called it as a bipartition of the graph. Clear? Now I'll draw some graph and you can check. Like I'm drawing a graph, this one. I'm drawing a graph, this one, and A, B, C, D. Is it a bipartite graph? Okay, let us check whether you can make a partition or not. Okay, I'll try. So I'm putting A and C in one set and B and D in another set. A and C to one and B and D in another one. Now you check A to B, there is an edge, A to D, there is an edge, and C to B and C to D. All edges I have done. So there is no edges in this set. There is no edges between this set. All edges are from in between, from this set to this set. So this graph is a This graph C4, this is basically a C4 graph. It is a bipartite graph, right? This graph is a bipartite graph. And I have drawn this graph in a little different way. This is also an example of C4. So this is a bipartite graph. Clear? Then I am drawing one more graph. Check this one. What is this graph? It is a C3. C3. It is a C3. And I am making it. Is it a bipartite graph? Is it possible? You try. I am putting maybe A in one set and B in the another set. But how I'll put C? Because C is adjacent to both A and B. So I cannot put C here, right? So therefore, this graph C3 is not a bipartite graph because you cannot make a partition. But C4 is. I'll draw one more graph, maybe C5. You check whether this graph is bipartite or not. 1, 2, or maybe A, B, C, D, E. Is it a bipartite graph? You check. Maybe A, C, and what you will put? A and C, it is in one set, and another set it is B, then D, because B and D are not adjacent. But how I will put E? Because if I am putting E here, then there will be an edge between, because there is an edge between E and A. If I am putting edge E here, there is an edge between E and D. So E I cannot put. So therefore, this C5 graph is not a bipartite graph because you cannot make a partition of it. But if I have a C6, graph, you can certainly make the bipartition A, B, C, D, E, and F. So A, C, and E. If you put A, C, and E in one set, B, D, and F in another set, A, C, E, B, D, F in another set, you can make the partition. The graph is bipartite. Right. So what is your final observation? C3 not bipartite, C4 bipartite, C5 not bipartite, C6 bipartite. That means what? If it is an odd cycle, it is not bipartite. If it is an even cycle, it is bipartite. Correct? Then with this observation, we have this theorem called a graph is bipartite if and only if it does not contain an odd cycle. A graph is bipartite if and only if it does not contain an odd cycle. Right? Because if you have a odd cycle into it, you cannot make that portion as a bipartite case. Clear? So I'm giving some example. You can now clearly tell me without wasting your time, you can say that whether the graph is bipartite or not. This graph, is it bipartite? No, no odd cycle, bipartite. Now I'm adding one more edges into it. Is it bipartite? Still it is bipartite because there is no odd cycle in it. It has some cycle. It has some cycle. Maybe this one is a cycle 1 2 3 4, but it's a even cycle. It has another cycle, this one 1 2 3 4, but it's even one. So it is till now it is bipartite. Right? Now I'm changing the graph. I'm giving one more edges into it. Now is it a bipartite graph? No, it is not. Why? Because I have an odd cycle involved in it, C3 involved in it. I cannot make it a bipartite because C3 is an odd cycle. Or I have another way also, 1 2 3 4 5. It is not at all a bipartite graph. I hope this is clear, right? So this is not a bipartite graph. So this may be one more example. One more example I'm drawing. Is this graph is a bipartite graph? Yes, it is a bipartite because there is no odd cycle involved in it. By the previous theorem, I can say. Is this graph is bipartite? No, it is not. Why? Because I got a odd cycle involved in it. I hope this is clear. So this is, then next is complete bipartite graph. The another one. Now again from the word, it's a complete graph, but by keeping the bipartiteness property. So I have in bipartite graph how it looks like. It is one set and another set, and the edges are from one vertex to the another vertex, right? Now complete means you have to keep on adding the edges till now it's complete. Till now it's you can like all edges you have finished. Now this is a complete graph. You cannot add one more edge by keeping it simple, right? It is the example of K32. So that means one side you have 3 vertices, in another side you have 2 vertices, and it is complete. All edges are done. K32. Similarly, draw a complete bipartite graph K33. How it will look like? 33. This all edges. You have to do all edges. All edges are done. Whenever it is done, you can say. Now it is a complete graph K33. I hope this is clear. Similarly, you can draw K24. That means one side 2, another side 4. And you have to add all the cases. Right? That is how you should draw a K24. All done. So this is how K24 you can draw. Right. So if you have understood, can you tell me what is the number of vertices in KMN graph? Yes, definitely it should be m plus n, because in one set you have m, another set you have n number of vertices. What is the number of edges? E of KMN. Number of edges is, you check that from each vertices how many number of edges are coming. From the other side, how many number of vertices are there? That many edges. So KMN is equal to number of edges in KMN is m into n. Clear? So this is the definition of complete bipartite graph. And number of vertices, number of edges, example of graphs, all are done. All the content I have taken from this book only. Kenneth A. Rosen, Discrete Mathematics and its Application. I hope you enjoyed the video. I hope these are helpful. If you like the video, press the like button. If these videos are helpful for others, you share with them. You also subscribe so that I will also get some motivation to make this video. Thank you very much. I'll come up with the next video in the next lecture. Bye-bye.